Next one I'm reading from is from the Mastering Chemistry. It is number, looks like 33. So problem 33, and it gives us the following. Part A, we have a 0.13 molar HF solution. Part B, we have a 0.13 molar NaF solution. And part C is a mixture of both. Part A will be an equilibrium expression where we need the Ka for hydrofluoric acid. Part B, we're going to need a Kb for the fluoride ion, and in part C, we're going to use the Henderson-Hasselbalch because we have a mixture of a buffered system, an acid with its conjugate base. Part A, we needed a Ka value, and I went back into the book and I found our list is at 667, I believe, is the page that gives us the Ka constants. Ka for HF, it reports as 3.5 times 10 to the negative fourth. Part B, the fluoride will be acting as a base, so turning the Ka into a Kb, we use the ion product constant for water and end up dividing to turn Ka into a Kb. Whoops. And in part C, we'll be using the Henderson-Hasselbalch, where we'll need the pKa. We can do that by negative logging up above. So we'll go to work representing part A first. When HF is placed into water, it forms an equilibrium that produces the hydronium ion and the fluoride ion. Concentration here is 0.13 molar. Let's call the value of hydronium X, and the fluoride ion will be X. We'll set that equal to our Ka. We looked up in our textbook. 3.5 times 10 to the negative fourth, the value of Ka, is X squared over 0.13 molar. Let's pull out the value of X, knowing X stands for hydronium. 3.5 e negative 4 times 0.13, square root that answer, just to share what my screen says so far. 3.5 e negative 4 times 0.13 got me X squared, square rooting that, and my value of X, 0.0067. That's hydronium. Negative log that answer, and we'll get a pH of 2.17. Look at the chemistry for B, sodium fluoride. It's that negative ion that will undergo hydrolysis, producing its conjugate acid, HF, and a base ion of hydroxide. Concentration of fluoride was 0.13 molar. Let's call the value of HF the value of X, and hydroxide now will also be the value of X. And we need a Kb because clearly fluoride is producing the base ion. Kb is taking Kw over Ka, where Kw is the ion product constant for water, 1 times 10 to the negative 14th. Set that over the looked up value of 3.5 times 10 to the negative 4th. Kw divided by Ka is the expression for Kb. We needed a Kb because we're making the base ion. Set that equal to X squared over 0.13 molar. All right, let's simplify. Solve for X. X is standing for hydroxide. So 1e negative 14, that's our constant called Kw, divided by 3.5e negative 4. They looked up Ka value for HF, and there's my Kb, 2.85 e negative 11. We'll cross multiply that with 0.13, the concentration of the original fluoride. Now we have on our screen the value of X squared, square root that answer, and there's the hydroxide concentration. Again, X is the base ion. When we negative log that answer, we get something called the POH. 14 minus the POH, and we'll find our pH of a base solution 8.28, depending on how you round there. I'm not sure how many sig figs they want. And in part C, we're placing in Henderson-Hasselbalch. We're going to place in concentration of two conjugates. That, by the very definition, is a buffer. pH is equal to the P, which is negative log of the Ka. 3.5 times 10 to the negative fourth. This is our expression for pKa, plus the log of the ratio of base over acid. They are of equal concentrations, so that simplifies to 0.13 over 0.13. Negative log of the Ka value, 3.5 e negative 4. And that's our pKa, 3.46, 3.4559, plus the log of the ratio of a constant number, so we'll hit it, plus the log of 0.13 over 0.13, and you can see that's simply going to cancel. So pH is 3.4634. I'm not sure how many pH units, decimals they'll want. Alrighty, so Henderson-Hasselbalch for part C, where we're looking at a conjugate pair acting as a buffer system.